Such a good jam. Thank you, Jen. Good afternoon, everyone. I'm Morgan Gregory, and I am so excited to be here with you today because I have the privilege of working on some of the most interesting and innovative science and space projects we have at Google Cloud. Let me give you an example. Sometimes, in the middle of a conversation, I'll stop myself and think, are we really talking about what it would take to build a data center on the moon? Or what an atmosphere of a distant planet would have to look like to support life? I have to pinch myself. It sounds like science fiction. And here's a question that comes up surprisingly often, and I'd like to ask you today. If you were given the opportunity to go up to space in a rocket, would you take it? Show of hands? Oh, wow. OK, interesting. Well, I don't have a rocket, but in the next 25 minutes, I do want to take you on a journey from Earth to the moon to the sun and beyond. And what I hope you'll see as we're zooming around space together is the magic that can happen when you bring together experts in a certain domain, in this case space, and experts in technology, and allow them to collaborate and co-innovate using Google Cloud. Let's get started. For the past 2 years, Google Cloud has been working with NASA's Frontier Development Lab. This AI research initiative brings together top researchers from around the world, from both physical sciences and machine learning. Over the course of 8 weeks, teams of experts tackle a set of challenges developed to support space exploration and discovery for the good of all humankind, all powered by Google Cloud. I'll share a challenge on each stop of the journey. The first one is here on Earth. It's floods. Now, floods are one of the most common, widespread, weather-related natural disasters globally, and they're increasing in frequency over time. Each year, floods are responsible for an average of 140 deaths in the US alone, and more than $250 billion in economic losses globally. Think structural damage, health-related costs, and agriculture loss. When planning for floods, the USGS, which is the United States Geological Survey, states that there are 3 key questions that must be answered. The first, what areas will be flooded? The second, how deep will the floodwaters get? And the third, when will the flood arrive? Now, the answers to these questions are predictions. And predictions are what machine learning is all about. So I'd like to take just a couple of minutes to talk about machine learning. In machine learning, there are 2 main approaches: supervised learning and unsupervised learning. We'll come back to unsupervised learning on the moon. But for now, supervised learning is where you build and train models in which you have data with labels, like answers. It's probably easiest to describe with an example. So let's say we were to build a model where we were going to try to take an image and understand whether or not it was a blueberry muffin. If we give the model enough pictures of blueberry muffins and tell the model that these are pictures of blueberry muffins, then over time, it starts to understand what makes a blueberry muffin. So once we've built and trained our model, we can then give it a new image, one without a label, and it can predict whether or not that image is a blueberry muffin. So it's helpful here to point out that machine learning predictions won't always be right. Models come with a certain accuracy, a set of false positives and false negatives. This is a false positive. We've predicted it's a blueberry muffin. Clearly, it's not. So we have to give our model, I love this data set. We have to give our model more than just pictures of blueberry muffins for it to understand what is a blueberry muffin and what isn't. You can see we're getting a little bit more representative in our data, but we all know that there are more than just blueberry muffins and chihuahuas in the world. I personally don't think our model will hold up very well to a picture of a chocolate chip cookie. But on to our floods challenge. So this team, they took not 1, but 2 of the USGS's key questions. And their challenge was to build a model of higher accuracy than the ones in use today. So that's fewer false positives and fewer false negatives overall. In this case, false positives are bad. That's when you're predicting that there will be a flood, but there is not one. And they're bad because over time, people can start to ignore evacuation warnings. We don't want to be the girl who cried wolf. And false negatives, well, they're bad too. You've predicted that there's not going to be a flood, but in fact, there is one. And then you've lost the opportunity to give people early warning for evacuations. So let's talk about the co-innovation that happened here. The domain experts, they brought to table a knowledge of data that could be predictive of floods. Things like accumulated rainfall data, satellite imagery on land use and topography, and river basin characteristics. Things like vegetation or impervious surface area, which is pavement, or even soil type. Things that tell us something about how fast water can drain into soil. Now, they also brought with them knowledge of a data set that could give us the labels. This is a stream gauge. What this does is it measures water level and water flow. So that can give us a label, flood or not flood. The USGS, they maintain over 10,000 of these stream gauges across the country. The technology experts on this team, well, they brought with them understanding and knowledge of different machine learning models that would be fit for the job. For those of you who are curious, multi-layer perceptrons, convolutional neural networks, gradient-boosted decision trees, and random forests. Now, the results that these teams were able to achieve in just 8 weeks was pretty incredible. They were able to build models that improve the accuracy of both of the two questions. This is the where question. What you're seeing on this map are the dots are where they've predicted where there might be a flood, and the blue ones are the ones where they've actually predicted accurately. And they also improved the accuracy of the models that were to predict when the flood would occur. What you're seeing here is on the left side, given an extreme weather event like a rainfall, they were able to predict the time when it would hit the peak water level, so essentially the flood threshold. Amazing results for just 8 weeks, as I mentioned. But going back to that USGS data, these stream gauges were only in 10,000 locations across the country. That doesn't cover the United States, and it doesn't even begin to touch on the issue globally. So the team also suggested ways in which they could improve in the future. They suggested that you could use high-resolution top-down imagery from satellites to give you the label, to see how deep the water was. Do you see the beaches and the sandbars appearing and disappearing? Machine learning models are great for picking that up. There's lots of opportunity here in floods, but more challenges await us on our journey. So on to our next stop. I'm going to take you 238,900 miles away to the moon. It seems like a pretty far distance, but we're traveling at the speed of light. It's only going to take us 1 second. With the Artemis mission, NASA is building plans to put the first woman and the next man on the moon by 2024. But we're going back in a different way, not just for a quick visit, but to build infrastructure that allows humans to stay for long durations, to learn how to learn on a different surface so we can ultimately go to Mars and maybe beyond. Do you see what I mean about sci-fi? Now, in order to do this, we're going to need to understand what resources are available to us on the moon. It would be very expensive and extremely difficult to ship all of those raw building materials up from Earth. So this next team's challenge was to build a model to predict where there might be metal on the moon. And why metal? Well, metal will be one of those key resources in building a lunar base. Currently, the only metal that we know for sure is on the moon is the metal that we brought with us on the Apollo missions. Well, we know where this metal is, and there isn't enough space garbage to build a lunar base, so we're going to have to look somewhere else. Let's look at craters. The domain experts, they brought to table the knowledge that metal could be deposited on a surface via a metal meteorite. When a large meteorite goes hurtling through space and hits a surface, it leaves a big hole, and that hole is a crater. So a crater could be a really good place to look for metal on the moon. So I want to introduce you to a crater. This is Tycho. Tycho is a crater on the near side of the moon. It's 53 miles across, more than 15,000 feet deep. So now that you're acquainted, does Tycho contain metal? Can you tell? Well, if you can, please call NASA because they need your expertise. Because we can't tell if there's metal in a crater just by looking at it, we need to bring more data to the table. The technology experts on this team use a technique called data fusion to do just that. Now, let's take a look at what additional data on top of Tycho looks like. This is an elevation map on Tycho. The green and brown areas are areas of higher elevation. The blue areas are areas of lower elevation. This is a rock abundance map on Tycho. The blue areas are more smooth. The red and brown areas are more rocky. This is a heat map on Tycho. The green areas are cooler. The red and brown areas are more hot. Now, the team, the domain experts, they prioritized thermal and magnetic data, their hypothesis being that these would be more predictive of metals. Now, if we take thermal, for an example, it's easy to follow their reasoning. Metals are good conductors of heat. It's why we cook with wooden spoons instead of metal spoons, and why I never understood metal slides at a playground. Now, you can imagine the same thing happening on the moon. As the sun hits the moon from different angles and in different intensities throughout the lunar day, the metals, the temperature variations of the metals, would look very different from those of the rock. It would be anomalous. It would stand out. But we still don't know if there's metal in Tycho, even with this additional data. We would have to physically go up to the moon and sample the materials of Tycho to understand if there was metal there or not. And we haven't been back up there in almost 50 years. So this is what we call unlabeled data. We can't give it a label has metal or does not have metal because we just don't know. But luckily, finding patterns in unlabeled data is exactly what unsupervised learning is for. So the team built and trained models using techniques like, for those of you who are curious, principal component analysis, PCA, clustering, and deep learning on top of Google Cloud. And in this way, they were able to isolate 7 distinct patterns, each representing a different anomaly. So for example, if you take a look at the bottom left, there it is, that crater's name is Q, introducing you to another crater. What you're seeing is a bright crater overall with a very bright and magnetic center. So that's an example of one of the patterns that they found. The idea is that we can then go to the moon and sample the materials at a specific crater to see what metals are present, if any. So let's say, for example, you were to go to the moon and sample a crater of crater type 4 and found that there was nickel there. Well, that would tell you something about the probability of there being nickel in other craters of crater type 4. Now, this is a really important step in understanding what lunar resources are available to us and where. But we don't have that base on the moon right now, so we can't stay any longer. It's time for the next stop on our journey. I'm going to take you about 93 million miles away to our sun. It sounds far, but again, traveling at the speed of light, it'll only take about 8 minutes and 20 seconds. Okay, I want another show of hands. How many of you have heard of space weather? Oh, wow. Okay, so I had never heard of space weather before the summer. So for those of you that have, bear with me for 1 minute. And for those of you that haven't, here's a quick intro. So aside from emitting a continuous stream of plasma called the solar winds, the sun also periodically ejects billions of tons of matter in what are called coronal mass ejections. Now, when this comes towards Earth, it creates magnetic storms in the magnetosphere and the upper atmosphere. That whole complex system, that's known as space weather. But what does this actually mean for us? Well, I have some good news and some bad news. First, the good news. Space weather is responsible for one amazing light show, the auroras, the northern lights and the southern lights. Now, I actually went to Iceland about 2 years ago. This has been on my bucket list for a long time, seeing the auroras. And every night, I hope to catch a glimpse of these beautiful lights. And every night, I didn't. I thought it was bad luck. What I didn't realize at the time was it was really a lack of coronal mass ejections. But what I also didn't realize is that I was able to reliably navigate around a foreign country using Google Maps and GPS navigation, also due to the lack of space weather, which brings us to bad news. Space weather is responsible for disturbances in GPS navigation. Now, aside from getting us to work in the morning and navigating around foreign countries, GPS is also responsible for planes landing safely, and in the future will be the cornerstone of autonomous driving. The disturbances can be as extreme as complete loss of signal or as simple as degraded performance. But knowing when and where this will happen allows us to work around these disturbances. Take the plane example, an airplane landing. If a pilot were to know when and where the GPS were to be unreliable, they could choose to either delay landing or fall back onto a different system to land a plane. So this team's challenge was to better predict GPS disturbances caused by space weather. The domain experts, well, they brought the knowledge that physics-based models, like the ones we use on Earth for predicting Earth weather, they just wouldn't hold up to the complex system that is space weather. But they also knew all of the ways in which we experience space weather, the auroras and GPS disturbances being the two that they chose to focus on. So they took these two symptoms, and they wanted to see if the shape of the auroras was predictive of the time and location of the GPS disturbances. The technology experts used a supervised learning technique, much like our blueberry muffin example, but this time using images of the auroras labeled with GPS disturbance data. You may be sensing a theme. The results that they were able to achieve were pretty incredible. So they were able to improve upon the current methods to give accurate predictions within plus or minus 5 minutes, which actually resulted in 15% improvement in prediction timing. And the team did this using only single images from a single source, a single camera. But we take pictures of the auroras from a ton of different places in the Northern Hemisphere. So they suggested you may be able to stitch together these images to create a more complete or holistic map of a magnetic storm, suggesting that it could lead to higher accuracy and better predictions. Well, I hate to leave the auroras, but in the few minutes we have left together, I want to take you on one final leg of our journey. We're going to leave our star and travel more than 24 trillion miles away. I don't know about you, but that means nothing to me. It is a totally meaningless measure of distance. Going at the speed of light, it will take us more than 4.2 years. Remember, it was 8 minutes to get to our sun. It's the distance to the next closest star. We are going in search of exoplanets. So exoplanets are planets orbiting around distant stars. We have 8 orbiting around our own star, and many of the stars that you see in the sky also have planets orbiting around them. By studying them, we can identify which planets are most suitable for life, and therefore where we should search for life. I know, again with a sci-fi. This team's challenge was to identify planets orbiting around those distant stars. The domain experts brought with them knowledge of the transit technique. You know what this is measuring the slight dimming of the light coming from a star when an object passes in front of the star and between the star and Earth. Now, that passing is called a transit. And when that transit happens at regular intervals and lasts for a fixed length of time, then there's a high likelihood that what you're observing is a planet orbiting that star, passing in front of it once every orbital period. The domain experts also brought with them knowledge of false positives. So when you might think or you might predict a planet, but really it's something else, like when we predicted a blueberry muffin, but we really had a chihuahua. So 3 potential sources of false positives are eclipsing binaries, and these are binary stars. So when you have 2 stars orbiting each other, you can imagine that the intensity and the amount of light that you're observing changes as stars pass in front of one another. The second source here is what they call background eclipsing binaries. So when you're measuring the light, you're measuring kind of a postage stamp-sized view. And if you have another eclipsing binary system in the background, it can also change the amount of light that you're seeing. And then the third here is stellar activity. These are things like sunspots, or star spots in this case, areas where they're cooler for a temporary period of time, leading to less light, or flares, where it's temporarily hotter, leading to more light. Now, the technology experts, they improved upon an existing machine learning model called AstroNet. So they incorporated this domain knowledge, the knowledge of these potential sources of false positives, and they incorporated them into AstroNet's deep convolutional neural network using Google Cloud. And I must be sounding like a broken record, but the results were amazing. They were able to improve the accuracy of the model, which led to a 50% decrease in model error. But the thing that I think is more interesting is it led to a 20% higher recall for Earth-sized planets. So the model previously, they were working on the same data set, the Kepler data set. And the previous model, Astronet, had identified a number of planets, but they're all much bigger. And these Earth-sized planets, they have a lower transit signal-to-noise ratio. It's difficult to tell if what you're seeing is actually a planet. But by incorporating this new domain knowledge, they were able to find more planets in the same data set. So they thought, even with these preliminary results, there probably were some more planets yet to be discovered in that data. Well, this is the last stop on our journey. I hope that you were as inspired as I was by what these teams were able to achieve just by bringing together experts in a certain domain with experts in technology and allowing them to co-innovate using Google Cloud. If you want to learn more about any of the challenges that I shared with you today, you can check them out, cloud.google.com/nasa.fdl. This is the marketing part of the speech. I'll tell you right now, if you go to that today, the only challenge that you'll see is the Exoplanet challenge and a sister challenge, which was called astrobiology. The other three challenges, the Earth, the Moon, and the Sun, those were all from this year, and those teams are actually still finalizing their papers. The results are preliminary, and they're putting together papers by the end of this month, I believe. So if you keep checking back, we'll have more information and more great results to share on that site later. Now, before I go, I need to bring you back down to Earth. But I want to invite you to my dinner table 3 weeks ago. So why to my dinner table? Well, my 3-year-old has been pretty into space lately. I mean, what 3-year-old isn't, right? This is actually a painting that she did. That's the sun and our planets. As a side note, I'm pretty proud that when I ask her what our sun is, she tells me a giant ball of flaming gas. Anyway, at dinner a few weeks ago, she asked me if we could go up to space in a rocket ship. She was pretty clear, the entire family would go, even her baby sister, and she would be the driver. She later told me that I could carry a gas can. Now, I asked all of you what your answer would be, but I never told you what mine was. My answer? Hard pass. No way. I've watched the Apollo documentaries. That sounds terrifying. But of course, I said yes. I mean, what other answer is there to your 3-year-old? Well, until that day comes, this innovative work is my ticket to space exploration.